So in our previous class, we were discussing about the solubility of solid in liquid. Then we had started with solubility of uh, gas in liquid. Okay. So we had stated, so we were discussing about the vapor pressure, right? Previously, we were discussing about what? We were discussing about the vapor pressure. So how the vapor pressure is exerted by the vapors on the surface, right? So we have also seen what is the dynamic equilibrium, how the dynamic equilibrium is reached. Okay, so the rate of evaporation will be equal to rate of condensation. So like that, the dynamic equilibrium is reached. Okay, and the vapors which are created due to the volatile liquid. Okay, so these will exert the pressure on the surface, right? So this was something called as vapor pressure. So related to vapor pressure, we were discussing some of the factors which affect the vapor pressure. So temperature, as we were discussing about temperature, so temperature, as you increase the temperature, okay, what will happen to vapor pressure? Right. So there will be a rise in the vapor pressure also, because as you increase the temperature, what will happen? The number of vapors which are produced will be more. Okay. So as a result, there will be rise in vapor pressure. So remember that whenever we are discussing about vapor pressure, and okay, and when you increase the temperature, so vapor pressure is directly proportional to temperature. So keep this point in your mind. Okay. Okay, so what will happen as so as you know that, so if this is a container, okay, which consists of the liquid, volatile liquid, okay, and what you have done, you are supplied the heat, okay, you have supplied temperature. So what is happening, the at the surface, so the molecules of the volatile liquid will be present. So as you heat it, these molecules will form the vapors. Okay, so they will form vapors, and these vapors, what will happen due to increase in the vapors? So they will slide to collide with each other. Okay, as there is rise in temperature, so these molecules, okay, they will gain some kinetic energy, and they will move faster. Okay, and due to this random motion, there will be increase in vapor pressure. So this is about temperature. Then second thing, we were discussing about the this what how it affects the vapor pressure is nature of liquid. So nature of liquid also plays a important role, okay, in affecting the vapor pressure. So this also we have discussed. So in a beaker, okay, if I take a liquid, okay, so the liquid, so depending upon the type of liquid, so if the molecules of the liquid, they are held weakly. Okay, so how these are held? These are held, okay, hello. So these are held due to the intermolecular forces. These are held with a force which are called as intermolecular forces. And due to the presence of this intermolecular forces, what will happen? If there are strong forces, okay, it is very difficult to break down this molecule. Okay. And if there are weak forces present between the atoms, then what will happen? It will be easily broken. Okay. The bonds can be easily broken. So weaker the intermolecular forces, okay, weaker the intermolecular forces, what will happen? More will be the vapor pressure. Okay, more will be the vapor pressure. So as what will happen, as the force between the molecules are weak, because if a weak bond is present, what will happen? The force between the molecule also will be weak, and as a result, we can break it easily, and vapors can be formed easily. Okay, and if vapors are formed easily, then vapor pressure also will be more. So this is in case of weak intermolecular forces. Same way with respect to strong intermolecular forces. Okay, if you have strong intermolecular forces, then it is very difficult to break. Okay, and the number of vapors formed will be less. As a result, there will be vapor pressure exerted will be less. Okay, so nature of liquid also plays a important role. Is it clear? Yes. Is this clear? These two factors are clear. So two more factors. So this we had discussed. Yes. Okay. So this we had discussed in our previous class. Okay. So now we are going to discuss the further part. So the further part, it is about what? Uh, so how the vapor pressure is related here? Vapor pressure, it depends on what? It depends on intermolecular forces. So if intermolecular forces are strong, okay, if the intermolecular forces are strong, then then the vapor pressure will be more. Okay, if the is strong, then vapor pressure will be less, and if the intermolecular forces are weak, then the vapor pressure will be more. So vapor pressure is inversely proportional to intermolecular forces. So if the intermolecular forces are weak, okay, then vapor pressure will be more. If the intermolecular forces are strong, then vapor pressure will be less. So this is the relation. Okay. Next, we'll go with the third factor, that is boiling point. How the boiling point will affect. Okay. So liquid which are having lower boiling point, okay, they will have higher vapor pressure. So remember this, the liquid which is having lower boiling point, the liquid which is having lower boiling point, they are having what? They are having higher vapor pressure, because these liquids with lower boiling point can easily be converted into gaseous. Okay, so the liquids whichever are having lower boiling point, these can easily be converted into what? Gaseous form. So lower boiling point, okay, they will create more vapor pressure, because you can easily convert into gas, and gas can be easily converted into vapor. Okay, so how it is related? So vapor pressure is inversely proportional to boiling point. Okay, so so low boiling point, more vapor pressure. Yes. So if the boiling point is low, what will happen to the vapor pressure? Vapor pressure will be high. Okay, so this is the conversion of your boiling point. Okay, this is your conversion of what? Boiling point. So boiling point. So if the lower the boiling point, what will happen to the this vapor pressure? Vapor pressure will be high. Okay. So low boiling point, as you know, low boiling point, it can be easily converted into gaseous form. Vapors are more, then vapor pressure will be high. So this is the third point. Fine. Next is the fourth one is purity of liquid. Okay, next is what? Purity of liquid. Next is purity of liquid. Okay, so purity of liquid, how you can state? So pure liquid. So whenever you have a pure liquid, so pure liquid will have higher vapor pressure. Now suppose I take an example. So suppose I have a two beakers, okay, closed beakers. Now here in this I have taken a liquid A, okay, pure liquid. So this is a pure liquid. Pure liquid means nothing is mixed in this. Okay, it is only one liquid. And in another beaker, I'm taking solution. Now solution means what? Solution means one this solute and solvent both are present. Right? Solute and solvent both are present. So this is not pure. Right? You cannot say this is pure. These it is okay, it is mixed. It is not pure, but pure liquid it is pure. Okay, so this is pure A and this is solution B. Now what will happen? So pure liquid, okay, whenever you have pure liquid, so you know that the molecules of the pure liquid, okay, they will be present at the surface. So your down also will be there. But what will happen when the molecules, when the liquid, okay, volatile liquid, it is converted into vapors. First, the molecule which are present at the surface, okay, they will get converted into vapors. Okay, then the next molecules like that. So what will happen? So pure liquid, okay, what will happen? They will have more vapor pressure. Okay, they will have more vapor pressure as compared to the solution, because there would be in this pure liquid, there is no other molecules are present. No other molecules are present for their disturbance. Okay. Now in this, okay, at the surface, your one solution is present, okay, and your because in solution your both solute and solvent both are present. So at the surface, both your solute is also present and your solvent is also present. So when they are forming the vapors, okay, only the small what you can say, only the volatile whichever the volatile liquid is there, so that will form the vapors, and this vapors will be less in number, okay, as compared to the pure liquid, because these are all are at of one what you say, one type. Okay, your it is solution, because you have both solute as well as solvent, so the number of vapors found in the solution will be less as compared to that of pure liquid. Okay, so easily evaporation takes place in your pure liquid, and in solution there is less amount of this will be this. Okay, so remember this one sentence that, okay, this is general. Okay, that whenever pure liquid is there and one solution is there, okay, in which the vapor pressure will be more, in which case the vapors formed will be more. Yes, one is a pure liquid, another is a solution, in which case the vapors formed will be more. In which case vapors formed will be more. I have given you the example, right? So this is a pure liquid A and pure, this is a solution B. In solution, both solute as well as solvent is there. Yes, pure liquid. Okay, pure liquid will form because the molecules present are of the same type. Okay, and the solution, there will be one or two or more different molecules present, because solution consists of what solute as well as solvent. Okay, so pure liquid. So whenever pure liquid is there, so pure liquid vapor pressure will be more as compared to the solution. So pure liquid vapors formed will be more. So due to the presence of vapors, okay, the vapor pressure will be more. Okay, so this is with respect to the, so when we consider, so here the vapor high vapor pressure will be high, and in this case the vapor pressure will be low, because only small amount of vapors are produced. Okay, small amount of vapors are produced. So this is about your factors affecting the vapor pressure. So vapor pressure and the factors are clear. Any doubts still here? Vapor pressure and the factors. So we have discussed 4 factors. So it depends upon the temperature, okay, boiling point, nature of the liquid, okay, nature of the liquid, and purity of the liquid. So these are the okay, fine. So next. Okay, so next we'll go for the law. Okay, depending on the vapor pressure. So we have another law, that is Raoult's law. So today we are going to discuss about Raoult's law. Okay, so Raoult's law is a law which is okay. It is based on the what liquids. Okay, so now suppose I take a closed beaker. Okay, I have two liquids. I have two liquids. Okay, these both the liquids are volatile. What do you mean by volatile now? I have told you what are volatile. So volatile means what? These can form vapors easily. So both the liquids. So two liquids means both the volatile liquids can form vapors easily. So both can form the vapors. Okay. Now, so both the solutions. So this is a solution, right? Because two liquids are, so only one liquid is present, then it is called as a this what pure liquid. Now your two types of liquids are present, so this is a solution. So this is, so I'll mark this as liquid 1. Okay, and another color I'll take so that it will be, so this I'll like this. Okay, and this is a liquid 2. So liquid 2. Okay, so both these liquids are volatile in nature. So two types of vapors are formed. Now, for any volatile substance, okay. Now, what is the Raoult's law? For any volatile substance, the partial vapor pressure, okay, the partial vapor pressure exerted by vapor on the surface of solution, okay, on the surface of solution is directly proportional to its mole fraction in solution. So this is what? This is your Raoult's law. This is what? This is your Raoult's law. So the pressure which is created, the pressure which is exerted by the vapor on the surface, okay, on the surface of the solution. Now we know now how the vapors are created, how what is vapor pressure. So these things we have discussed previously now. Okay. So I'll not repeat it again. So this vapor, okay, the pressure which is exerted by the vapor on the surface of the solution, this is directly proportional to what? It is directly proportional to its mole fraction. It is directly proportional to its mole fraction. And how this mole fraction is given? Mole fraction is given as uh, psi. Okay, so this is the psi. So now when we are denoting the this now how we had related this to Henry's law, right? We had related to Henry's law, but Henry's law is different and this is different. Okay, now here, now in Henry's law, what we did, we removed the proportionality sign and we had introduced what? We had introduced the constant KH. Okay. Now, what you have to note that that at least, so here both the solutions are volatile in nature. Okay. Now, when you are taking the this Raoult's law, okay, the necessity is that at least one of the component should be volatile. Okay, for the application of the Raoult's law, at least one, either one of those liquid should be what? It should be volatile in nature. It should produce gas because we are studying about gas in liquid. Okay, we are discussing about what? Gas in liquid, right? So now, as we know, partial pressure, okay, that is a vapor, that is a what? The partial pressure, vapor pressure exerted by the vapor, okay, on surface solution is directly proportional to its vapor pressure. So P is directly proportional to this chi, okay, psi, and this psi is nothing but it is a concentration term. Okay, it is a concentration term, and we know that concentration term we have taken a mole fraction. Why we are taking mole fraction? Because number of moles can be calculated easily, right? So mole fraction, we are introducing mole fraction. So how we calculate mole fraction of a particular component can be calculated. So if I want to calculate the mole fraction of chi A, okay, component A, then it will be mole, number of moles of A upon total number of mole, okay, total moles. So this is the so because of that we are taking the mole fraction because we can calculate each component. We can calculate the number of moles of each component. Now, what is happening? Okay, so either of this will be, so we know that one more fact that, okay, whenever mole fraction is there, so the how many, the number of components, the total number of components present, okay, it should be equal to 1. So chi A and chi B is equals to 1. So this you have to keep in mind. Okay, so chi A plus chi B is equals to 1. So this is your what? This is your the total number of component present, okay, should be equal to 1. Now we'll write the Raoult's law. So just a second. So when we are writing the Raoult's law, so P is directly proportional to chi. Now what we are doing? P naught. Okay, what is P naught of A? P naught of A is nothing but it is the component in pure state. Okay, whenever you have component A in a pure state. So we'll write for component A in a pure state is equal to chi A. Okay, now when we are removing this, okay, so what we have to do? So P uh, so P naught of A is equals to, or we'll introduce this chi A later. Okay, you don't get confused. So, okay, so PA, so the partial pressure of component A is directly proportional to mole fraction of A. Now, when we are removing this proportionality constant, then we will take a proportionality sign, we'll introduce a K, okay, and chi psi A. Okay, now we know that so from XA, that is psi A plus psi B equals to 1. Okay. So psi B will be equal to what? Psi B will be equal to 0. Okay. So psi A plus 0 will be equal to 1. So psi A is equals to 1. So by putting this, so PA is equals to K into what is psi A? Psi A is 1. Okay. So PA will be equal to K. Okay. So what we have done here, So this Pa, okay, this is in pure state. So we are taking it as 0. We are putting a not on that. Okay. So if we introduce this here, if we are replacing this here, so how it will be? So P naught A is what? It is a pressure. It is a pressure, partial pressure in pure state. It is a partial pressure in pure state. So if I want to find the component, partial pressure of component 1, it will be what? Or component A, it will be P naught of A into chi of A. So this is a partial pressure of component A. Similarly, if I want to find the partial pressure of component B, it will be PB is equals to P naught B into chi of B. So this is the according to what? Raoult's law. So this is according to Raoult's law. So what is P naught of A and P naught of B? These are the vapor pressures of the liquid in pure state. Pure state means what? It has no other liquid in that. Only one type of liquid is present. So it is a pure state. And PA means what? There will be a solution. Okay, it is not in pure state. So some other molecule can also be present. So consider for a binary solution. Okay, if you have a binary solution of components, two components A and B. Okay, if I have a binary solution, binary means what? Binary means a solution consisting of two components. So, so we have two components A and B. Okay, then the component A is PA equals to chi of A. So because is equals to chi of A, and PB is equals to chi of B. Okay, so we know we know these terms now. So P naught of A is what? It is the vapor pressure of component A in pure state. Pa is vapor pressure of component A in the solution. Solution consists of solute plus solvent. P naught of B is the vapor pressure of component B in the pure state, and P naught PB is vapor pressure of component B in the solution. Okay, so this is the these okay, so here I'll write it. So these equations you have to keep in mind, okay, for two different components. Okay, is it clear? Is it clear? So we are going to see two cases. Okay, we are going to see two cases in this Raoult's law. Okay. So we are going to see two cases. Just a second, I'll take a file. Okay. So case one. Okay. Case one is what? Case one of the Raoult's law. Okay. Case one of the Raoult's law. So first is when you have a volatile solute, when you have a volatile solute plus volatile solvent. So when you have a volatile solute and volatile solvent. Now suppose, okay, suppose consider I have two beakers. Okay. Now in this beaker, I have solution A, and in this component, I have solution. This is a sorry. Okay, I'll take this as wait, another color. So this is a solute. Okay, so this is a solute. So you know that solute is present as what? It will be present in less quantity, right? And solvent is present in more quantity, right? So this is B. This is we are taking as B. Okay. Now solute means what? Solute is only one type. Solute will be only one type. Solvent also will be in the one type. Now at the surface, the molecules will be present. These molecules, as you know, okay, due to the dynamic equilibrium, they will produce what? They will, when the dynamic equilibrium is reached, okay, so vapors are created. Okay, vapors are formed. Now these vapors are these in pure state or are these in impure, means how they are? So these, because this is in what? It is a pure component A and this is a pure component B. Okay, solute is only one type of molecule is formed, and in solvent also one type of molecule is formed. So how do we denote this component A? So it will be P naught of A, and this we will write the vapors of solvent B will be denoted as P naught of B. Okay, so when we add solute and solvent, okay, when we add solute and solvent, for example, in sugar and water, okay, when we add sugar in water, what you will get? You will get solution. You will get solution, right? So, okay, so you will get solution. Now, what will be present in the solute? Okay, in the solute, the what will be present in the solute? Your your molecules will be present, vapors, right? And in your solute also vapors will be present. In solvent also your vapors will be present at the surface. Now, in the solution, when the solution is formed, okay, what will happen? What will happen in pure forms? As you know, in pure form the vapors formed will be more, right? So in this case, also the vapors formed will be more, and in solvent also the vapors formed will be more. Now, in case of solution, what will happen? So in solution, both your solute is also present and your solvent is also present. So at the surface, okay, at the surface, your both the molecules are present. Your solute molecules are also present, and your solvent molecules are also present. Then when they undergo the evaporation, okay, the surface phenomena, what will happen? They will form the vapors. Okay, vapors are formed. Now the number of vapors formed, what it will be? The number of vapors formed will be less. Okay, the number of vapors formed will be less as compared to that of your pure solute and solvent. So this is, so if I denote one of this as, so this will be denoted as PA because it is not pure. Okay, and this I will denote it as PB. Okay, because in solution, both your solute and solvent will be present. So the number of vapors present will be your less as compared to that of solute and solvent. So your more number of this is present here also, more number of vapors are present. Is it clear till here? Yes. Is it clear up to here? So what we have taken? We have taken one volatile. Both are volatile solute and volatile solvent. Only volatile solute and solvent can form the this what? Vapors, right? So in both the conditions, you can see that solute also can form the vapors and solvent can also form the vapors. Why? Because volatile liquid. So whenever you have volatile liquids, only volatile liquid can form the vapors. Okay, remember that only volatile. If you have non-volatile, they cannot form the vapors. Okay, so in both the case, so pure solute can they are also forming more vapors. Pure solvent also is forming more vapors. When you combine, okay, they form solution. So in solution, both type of molecules is present. So the process of forming the evaporation, in that what will happen? The molecules, the vapors form will be less as compared to that of the in case of the pure liquid. Okay. Now, when we want to, so these are its partial pressures also, right? So we have denoted the partial pressure. So this is in pure liquid. This is a pure liquid B, and this is a partial pressure of component A in the solution and component B in the solution. Now, if I want to calculate the total pressure, okay, in this solution, so how I can calculate? So I'll calculate by taking the sum of PA plus PB. So how much pressure is created in A plus how much pressure is created by B. So this is a partial vapor pressure can be calculated like this. Okay. So there is something called as uh, Dalton's this, you know, Dalton's theory, right? So what is Dalton's theory? So according to Dalton's theory, okay, so the total vapor pressure. So how you calculate the total vapor pressure? So total vapor pressure is equal to sum of the individual partial pressure exerted by each component, right? So when you want to calculate the total vapor pressure, okay, so you have to calculate the vapor pressure of each component. So component, how many components are there here? So component A, component B. So I'm taking the sum of both these components. So this is your Dalton's theory. So according to Dalton's theory, we are applying this. Now, suppose, okay, suppose you can take any condition, but here I am taking, what I am taking is condition here. Just a second. Okay. So suppose, okay, either of this. So here PA and PB are there. So both are equal, both are volatile. Now I want to take that a condition wherein P naught A is greater than P naught B. So I'm supposing it. Okay, I'm just taking an example. Suppose you can take either of this. You can take PB, P naught B is greater than P naught A. Okay, you can take any one condition. I'm taking this condition. Suppose P naught A is greater than P naught B. Means what? This means that solute is more volatile. So both are volatile. Okay. What I am supposing that both the solutions are volatile. Both the solute as well as solvent, both are volatile. Right. Now here in this condition where you can see that both are volatile. So either one should be greater. Right. Either of one should be greater. So what I have taken that P naught of A should be greater than P naught of B. So that is means what? Solute is more volatile than solvent. So this I am supposing. Okay. I'm taking suppose. And you know that always that pure vapor pressures are greater than the vapor pressure of the solution. So this also you know, this condition you know. So don't forget this. Okay, pure vapor pressure is pure liquid vapor pressure is always greater than solutions vapor pressure. So this you have to keep in mind. This we will be applying. Now we will apply this to Raoult's law. Okay, now you know that according to Raoult's law, according to Raoult's law. Okay, so we know that partial pressure is directly proportional to chi. Okay, so P naught or PA is directly proportional to psi A. Now, after removing this proportionality sign, it will be partial. This will be equals to P naught of A into chi of A. So this is our equation 1. Similarly, we have the component B. So partial pressure of B is equal to psi of B. So if we remove the proportionality sign, so this will be equal to P naught of B into psi of B. So these are our two equations. Now we know that from Dalton's from Dalton's theory, what we know that Dalton's theory that okay, Dalton's law, what we know that PT is equal to PA plus PB. That is, the total vapor pressure is equal to the individual vapor pressure exerted by each component. So it is PA plus PB. Now from, so this Dalton's law, it is applicable for non-reacting gases. Okay, non-reacting gases. So we apply this law only for non-reacting gases. So from PT is equals to PA plus PB. Now what we'll do, we will take from 1 and 2. So we have two equations, 1 and 2. So we will add it here. So how it will be? So PT will be equal to P naught of A into psi of A plus P naught of B into psi of B. Okay. Now we know one more condition that psi A plus psi B equal to what? Equal to 1. Right. We know this condition. Right. Now what we'll do, I want to express is in that P naught of A is greater than P naught of B. That is a solute is more volatile than solvent. Right. So this condition you don't forget. So what I want to do, I want to take everything in P naught A. That is in P component A form. Right. So now what I'll do here. So if I take this, so what will be XB here? So if I take XB here, so if I want to, XB will be here 1 minus, psi B is psi B will be 1 minus psi A, right? So therefore psi A. So now I will put the value. So PT will be P naught of A into psi of A plus P naught of B. So I'll put this value here. So it will be 1 minus psi of A. So I'm expressing in terms of A here. So what I'll do now? Now I'll take the So P naught of A into psi A plus, so I'll multiply this. So P naught of B into 1. So it will be P naught B minus, uh, it will be 1 minus psi A, right? So this will be psi A, okay, into P naught B, into P naught B. Fine. Uh, Now what I'll do? So, so P of T will be equal to, so I'll take what? PB common. Okay, I'll take PB common here. So I'll take PB not common. So if I take P naught B common, then what will happen? P naught B common plus, okay, plus psi A. So psi A will be common now. So P naught A, then plus psi A will be P naught A minus P naught B. Okay, is it clear? See here. So this is when you have P naught of A greater than P naught of B. Clear till here? Yes. Just see the steps, what all I have done. So this is where P naught of A is greater than P naught of B. Okay, I'm just supposing it. Okay, so we have two liquids, volatile liquids. So this is one case wherein both the solute and solvent are volatile in nature. Okay, what we are supposing that the solute is much volatile than your solvent. Okay, solute is more volatile than solvent. So if I consider this condition and apply the Raoult's law, okay, and then apply the Dalton's law. Okay, that is Dalton's law is the sum of the total pressure is equal to the sum of the individual partial pressure of each component. Then I will get this particular equation. Okay, where we have P naught of A greater than P naught of B. Now, similarly, okay, so similarly, if I consider if P naught of B is greater than P naught of A, okay, if I have P naught of A greater than P naught of B, then what will be the condition? The condition will be, so PT will be equal to, what will be the same procedure you have to follow, okay? So P naught of A plus chi of B, P naught B minus P naught of A. So this will be your, so anyone you can suppose, you can take anyone, okay? So whichever you are studying, study one only, okay? Don't get confused between two. So you study only one case, okay? Similarly, you can apply for the other. Whether a solvent is more volatile than solute or solute is more volatile than solvent. So like this, we can calculate the total vapor pressure exerted, okay? Is it clear? Is this clear up till here? So this is according to Raoult's law. This is according to Raoult's law. Okay. Up, up till here it is clear? Okay, fine. So we'll go to the next one. So now this, okay, after taking this, now we are going to study the graph. Okay, we are going to study the graph. So I'll just clear here. We are going to study the graph of Raoult's law. Okay. So now, okay, Raoult's law, that is graph of Raoult's law. Okay, for the solution containing, we are going to see the graph for solution containing volatile solute plus volatile, okay, solvent. So for this condition, we are going to see the graph. So what all equations we have seen? So P naught P A equals to P naught of A into chi of A. Then second equation we have seen is in the solving this. So P of B is equals to P into chi of B, and the third was total pressure, that is PT is equals to P naught of B plus chi of A into P naught A minus P naught of B. Okay, where you have P naught of A greater than P naught of B. So this is the condition. Okay. Now we will apply the graph. Now we will see the graph. So you know that when you are plotting the graph, okay, we have a what? We have a x-axis and we have a y-axis, right? We have a x-axis, we have a y-axis. So now here, so at the x-axis, what we have? At the x-axis, we have our mole fraction. We are plotting the graph. So at the y-axis, we have vapor pressure. Okay, vapor pressure. And at the x-axis, we have the mole fraction. Mole fraction denoted by chi. Okay, so at the x-axis. So this is the y-axis. This is your x-axis. Now here, suppose, so our condition, first one condition is what? When P, so we'll take the first equation now. Okay, we'll take the first equation. So our first equation is PA is equals to P naught of A into chi of A. Now, can you relate this? Is this the graph of the type y is equals to mx? Yes, is it a graph y is equals to mx? What is y is equals to mx? The graph will be through origin. Okay, the slope, this will be slope will be through origin, right? So it will pass through the origin. Now, if I take conditions like at xa, that is chi of a, if it is 0, okay, what you will get, and at chi of b, psi of b, if it is 0, psi of 1, okay, if psi of a is equals to 0 and psi of 1, psi of a is equals to 1. So what will be the conditions? So put these values. If psi of a is equals to 0, then p of a will be equal to 0. Right. And if psi of A is equals to 1, then P of A will be equal to P naught A. Right. Now, what will be the points? So here, so if psi is equals to 0, then both the points will be 0 and 0. Right. And if psi A is equals to 1, so it will be what? One will be 1, another will be P naught of A. So these are the points. So now first we'll draw this. Okay. So if I take now psi of A, so mole fraction A at 0. So 0 means it will be here. So I'll write it as psi of A is equals to 0 here. Okay. And here, so psi of A is equals to 1. We know that mole fraction psi of A plus psi of B will be equal to 1. So the total value of mole fraction will be equal to 1. So not more than 1. So psi of A equal to 1. Okay, I'll plot it here. So here it is. Now, what is happening at psi of A is equals to 0. P of A will be equal to 0. P of A equal to 0 means where it will be P of A, it will be this side. Okay, P of A will be equal to 0. Now, I'll take another color. Wait. Okay. So, so at psi of A is 0. So P of A will be 0. So this will be at 0 itself. Okay. Now, when the, so this is both is at 0. So no point. Okay. Then when at psi of 1, when psi of A, okay, when psi of A is 1, so 1 means it is here. Okay. You can see blue color dot. Okay. 1. Then P A is equals to P naught. So this is PA. So this will be P naught. So how it will travel? So how it will go? So P will be equal to PA. So it will be, so from here, I'll take in terms of. Okay. So it will be, this is what? P naught of A. Okay. So this will be P naught of A. So here I'll, so here also there will be a, so this is the origin. Okay. So this is your graph wherein this is your graph for first one, that is PA is equals to P naught A into psi of A. Okay. Now similarly, when I write, so this is your P naught of A. Okay. Now, similarly, if I write it for your, in the same graph, if we write the second, okay, second one, that is PB is equals to P naught B into psi B. Put the values at psi A equals to 0 and at psi B equals to, sorry, psi A. Okay, when psi B is equals to 0 and psi B is equals to 1. Yes, put the values now and see what you will get. Tell me what values you will get here. See the values. So you have to just substitute. Okay. What values you will get? So for at psi A is equals to 0. Okay. That is psi B is equals to 0. Then PB also will be equal to 0. Right. So if this is 0, 0 into 0 is 0, 0. Then when psi of B is equals to 1. So PB will be equal to psi naught B. So what are the points? This is 0 and 0. And this is 1 and this is 1 and P naught B. Okay. Now in the same, we will draw the graph. So I'll take the another color. Okay. Suppose now what we have to do, you have to consider this as your x-axis. Okay. Consider now this is as your x-axis only and this is your y-axis. Okay. For pressure. So for yours, now you forget this. You forget this. Okay. You forget this. Wait, I'll show you. This you forget now. Only you think about this and this axis. Understood? So just forget about this axis. Just see. Now you substitute. So at psi b is equals to 0. So it will be here, this point. Okay. I'm drawing with yellow. So when psi b, so this your condition is psi b equals to 0 and here it will be psi b is equals to 1. Okay. So when psi b is equals to 0, then your P naught of B will be equal to 0. Okay, P naught of B, PB will be equal to 0. Right. Now here, PB will be equal to 0. Yes, so this will be at origin. Then when psi of B will be equal to 1. Okay, when psi of B will be equal to 1, then what will happen? Then the graph will be passing through here. So it will be like this. So this is your P naught B. This is your P naught B. Okay, so this is your second graph. Now for the third condition where you have PT equals to P naught B plus P naught A minus P naught B into psi of A. So again put the condition like psi A is equals to 1. What you will get when psi is equals to 0 and at psi A is equals to 1. So when you have psi is equals to 0, then you will get PT will be equal to, so psi A, so this will term will become 0, so it will become P naught B, and at psi A is equals to 1, okay, what will happen? This will become 1 and this will be PT is equals to P naught A. So what will happen? So it will pass through this. So P naught is equals to PB. How it will go? It will go the straight line. Okay. So this is the for third one. So I'll write it here. So this is the Raoult's law. Okay. So this is the Raoult's law. So this is the second one. For PB is equals to P naught of B into psi of B. And the third one is your third one. Okay. For PT is equals to PA plus PB. So this is your Raoult's law. Now, you might have thinking why I have written PB down. Okay, I could have written up also, right? But what we have considered that P naught of A is greater than P naught of B. So because of that, as solute is more volatile than solvent, so with this condition, you can consider reverse also. You can consider P naught of B greater than P naught of A. So that time the conditions will be different. Okay. So your P naught of B will be higher than your P naught of A. Is it clear? Is the graph clear? So this is about the graph. Okay. So this is the graph of Raoult's law. So very important graph. You have to know what is the how to plot the graph. So this is the important part of law. Okay, that is Raoult's law. Is it clear up to here? Okay, so this was a case one. Okay, and this was a case one where you have volatile solute and volatile uh, solvent. Okay, both are volatile in nature. Now we are going to discuss case two. Case two, where you have non-volatile. Okay, you have non-volatile solute plus volatile solvent. You have volatile solvent. So this is another condition. Now here, suppose okay, so in this case, what is happening? So we are going to see how it is relative lowering of vapor pressure, how it is related. Okay, relative lowering of vapor pressure, that is RLVP. Okay, RLVP. It is relating lowering of vapor pressure. Suppose I have again two beakers. I have closed this two beakers. How I have closed it? So I have closed this two beakers. Okay, so that because there is gas involved, right? So this is the first one is pure solvent. So this is a pure solvent. In pure solvent, as you know, the molecules of the pure solvent will be present at the surface. Okay, so as it is volatile in nature, the solvent is volatile in nature. So what will happen to the this volatile solvent? What will happen if it is volatile solvent? Vapors will be produced, right? Vapors will be produced. This the vapor is in pure state, so I have written it as P naught A. Second condition, what it is? This is a solution. Okay, I have mixed the solute and solvent. Now here, how it is the condition? Just see. Okay, so I have solute. So this is my solvent. Now I'll add the solute into this. So these are my solute molecules. So solution consists of what? Solute, which is a non-volatile. Solute is non-volatile. Non-volatile means what? They will not form vapors. And solvent is volatile in nature, and this will produce the what? Vapors, right? Now, what will happen? Now, as the solvent is volatile in nature, so only the solvent will produce the vapors. Okay, so these vapors, how I'll represent? I'll represent as PA because these are not in pure state, right? These are not in pure state. Why? Why they are not in pure state? Because it is it is combined in solution. Okay, it is combined in solution because solute is also present. And what will be the vapors? In which state the vapors will be more in the pure state, or in the solution state, in the solution state. Okay, in the pure state, in the pure state, the vapors will be more as compared to that of the solution state, because in solution both solute and solvent both are present. We know that. So in pure, okay, vapor pressure will be more as compared to the solution. Okay, so this condition one you have to remember. So as the solute is non-volatile, they will not produce any vapor. Okay, so P naught of B will be equal to 0 and PB also will be equal to 0. Okay, non-volatile solute. So for non-volatile solute, as the condition, okay, as it is non-volatile, both the vapor pressure of the component B in pure state and in the solution state it is 0. Now we have to apply the Raoult's law for what? We have to apply the Raoult's law only for the solvent particle. So if when we apply the Raoult's law, okay, Raoult's law for the solvent, how it will be? So partial pressure, okay, partial pressure, vapor pressure will be directly proportional to psi of A. Okay, so when we remove this proportionality sign, so partial pressure will be equal to P naught of A into psi of A, right? Now, there is difference in vapor pressure. So there is a difference in vapor pressure. So in the pure state, the vapor pressure is different, and in the solution state, the vapor pressure is different, right? So we know that P naught in pure state, the vapor pressure will be more as compared to that in the solution state. So we are considering this. So how will we consider the difference? We know we can apply delta P. What is delta P? Delta P is nothing but the difference in the vapor pressure. So how the difference, always the difference is taken as higher minus lower, right? You know how the difference is taken, higher minus lower. So P naught of A is higher because it is in pure state. So P naught of A is my difference of PA. Okay. So now delta P. Delta means what? Delta means we are taking the difference. Okay. Difference in the partial pressure. So how it can be calculated as delta P naught of A minus P of A. P naught of A is in pure state and P of A is of solution state. So so delta P is equals to P naught of A. So if I put the value of PA, what is partial pressure of A? So I'll apply this. So it will be P naught of A into psi of A. So after applying this, so delta P will be equal to P naught of A minus. So what I'll take common? I'll take P naught of A common. Okay, so P naught of A common. And so what is psi of A? Psi of A is nothing but it is 1 minus psi B. You know this condition. This also you have to remember. So psi of A and psi of B will be always equal to 1. So if I want what is psi B will be 1 minus psi B. Okay, so if I put this condition, then delta P will be equal to P naught of A, then P naught of A 1 minus 1 plus XB. Okay, so delta P will be equal to P naught of A into psi B. 1 minus 1, it is cancelled, it get cancelled. So it will be psi B. So delta P. So delta P, if I take this transfer down, so it will be, so I am transferring this down. Okay, so this will move here. So it will be P naught of A into psi of B. Now what is delta P? Yes, students, what is delta P? Delta P is nothing but difference, right? So P naught of A minus P of A divided by, so this, okay, this I am going to apply into delta P equals to psi of B. So this is the relative lower pressure, how the relative low vapor pressure of the solute, okay, it is related to solvent. So we have calculated what? The mole fraction of component B, okay, which is the solute. So RLVP, that is the relative lowering of vapor pressure. It depends upon the amount of non-volatile solute. Okay, it does not depend upon the nature of the non-volatile solute. It depends on the amount. Okay, how much amount of non-volatile solute is present. So this is the case 2. Understood? Is it clear? Yes. So this is the case 2, wherein we are seeing a non-volatile solute and a volatile solvent. Okay, a volatile solvent. Is it clear, students? So we will see a graph and then we will stop. So how the graph is plotted? So pressure is taken here and mole fraction is taken here. So this is psi is equals to 0 and this will be psi of A is equals to 1. We know that the volatile, non-volatile solute is present. So we are not going to plot for non-volatile solute. We are only considering the volatile solute, solvent. Okay, that is PA, okay, partial pressure of A. So at XA is equals to, so if we have, so this condition, I'll write it here above. So PA is equals to psi A into P naught of A. So if you have at psi is equals to 0, what will happen? PA will be equal to, PA will be equal to 0, okay. And at psi A equals to 1, what will happen? PA will be equal to P naught of A. So it will be a straight line. It will be a straight line, okay, where P naught of A. So this is only the graph. So whenever you have a non-volatile solute and volatile solvent, this is the graph for your Raoult's law. Is it clear up to here? Yes? Any doubts? So in the next class, we are going to study about ideal solutions and what are non-ideal solutions and their graphs. Okay. Any doubts up to here? Yes? Okay. Others? Any doubts, students? So in the next class, we are going to discuss about the ideal and non-ideal solutions. So today, in today's class, we have seen the Raoult's law and the cases. Okay, we have seen the different cases. So in the next class, we are going to see about ideal and non-ideal gases. Okay, fine. So I hope there are no doubts. Okay. So if you have not understood anything, okay, please go through today again once. So if you have any other doubts, you can ask me in the next class. Fine. So I hope you have understood everything. So I shall end the session here. Okay. So we'll meet in the next class. Thank you.